Now, we also have a two-person that really had the inspiration for RICAIP and started all this. Besides Professor Magic, this was Professor Wahlster, who we're very honored to have here and present a speech on Edge AI for a sustainable Industry 4.0.
Yeah, thank you very much for the invitation and this great event here. I'm very happy to come again to Prague after a long period where we couldn't travel. Today I have a new topic for you, Edge AI for Sustainable Industry 4.0. Doesn't work. When we talk about sustainability, of course, the term circular economy is very popular today. And when we have circular economy in the context of Industry 4.0, what does this mean? It means that already in the design of a new product and a production process, we are considering energy consumption, of course, waste production, and also the emissions which come from our factory when we produce this object. Also, our technology of digital twins, which is now very widespread in Industry 4.0, helps us to really establish a full cycle in the circular economy. That means we store not only the CO2 footprint, but many other parameters, material parameters, just from the beginning. When we use, for instance, smart materials, they even can measure by integrated sensors a lot of factors from the environment. And this helps, of course, in resource-sensitive production, in so-called new use-based business models. We go more for leasing and sharing of our products. And from the design, we consider these new business models. And then a lot of what we call as-a-service offerings. You know this from software. And this is now a very big movement also in production. So I'm pretty sure that this is one of the key topics in the next decade of Industry 4.0. Everybody is discussing about climate change problems, about energy problems. Now with the war in the Ukraine and Russia, we have a big problem, at least in the German industry, with energy and so on. So this is very important to consider. And this means that we think much more than before, not only about recycling, but remanufacturing, about refurbishing production sites, about reuse and repair, of course. And we want to repair already during the production process. Many companies now in production throw away. If they have a problem with an emerging product, it's just waste. Next one, please. And this, in the long run, of course, we cannot tolerate. So we have to go to zero defect and zero error production, as I will show in a moment. When we conceived the concept of Industry 4.0, from the beginning, we said a smart production means not only that we have superior quality for high mix, low volume smart products, but we want to do this more and more as urban production. That means we want to have the factory inside the city and not a long way to go, because otherwise we again add to the CO2 footprint, because we have a lot of traffic of the workers from the city to the factory. And in Germany, we already have new factories built inside the city. In Stuttgart, for instance, in a neighborhood where there live a lot of people, there is an aluminum factory. Unbelievable 10 years ago. But this means that the workers can go by bicycle or walk to the factory and not drive half an hour to the factory. Also in Frankfurt, a new factory will be open next year in the middle of the town. So this is one trend, urban factory with zero emission, but then also what we call green production. That means very resource efficient factories, which from the beginning really reason about their own resource limitations and how they can optimize this. Last year, we had a C-level summit for Industry 4.0. I gathered all the C-level CEOs, for instance, or CTOs from big companies like Bosch, Siemens, they all were there because we wanted to give a clear message to our government that we started Industry 4.0 10 years ago, but this is not the end of the story, because such an industrial revolution cannot be done in 10 years. This is never in history happened. Minimum is 20 years. So we need the next decade, and fortunately our government has accepted this argumentation. So we go on, and this is important, but there is a little bit a shift in the attention and the focus points. And as you see here, sustainability is a big issue, but also interoperability, because we believe that we need more interoperability. We have things on the European level like Gaia X, IDS, and so on, but we have to go further. I will go into detail later in the talk. And then also, as I said, autonomy, because we learned the lesson now with the chip crisis and so on. I think and especially Czech Republic and Germany cannot rely too much on other countries outside of Europe if they have critical parts in their supply chain. And this is also a big issue for us, but also a chance. You know that semiconductor production was more or less closed down in Europe a few years ago, and now it's revived. Why? Because we see the effect when China doesn't deliver. And so these are the things. We had here in Dresden a very nice meeting of government officials, and Professor Masik was, of course, the representative from Prague, and it was decided that the platform which we already have should be extended. And one idea was IQAMA. Professor Masik has already mentioned it, and the idea is really towards zero production, in incremental quality control. So we want, in every production step, we are starting to check already the quality, not at the end of the chain. Today, if you go to a factory, for instance, in BMW, they use for each car about 20 minutes to check the car at the end of the production line. Then they find an error, hopefully not too often, but it happens. Then it has to be, to repair this, to go to the part which is wrong, you have to disassemble. And this costs a lot of time, sometimes 2 or 3 hours, because the whole process has to be repeated, and so on. How do we do this? It's a new approach. We don't just check the quality of the product in the sense that we do measurements and sensing, but we observe the actions, both of humans, human-to-human cooperation, of human-robot, and even when robots work together, we check whether they do the right thing. So you see here in this diagram very nicely that we do wrong action recognition with cameras, with variable sensors, with IoT devices, and even microphones. And this can be the individual action here of one worker, wrong step in the assembly, and this happens quite often, believe it or not. Even in really very professional companies like Bosch, we observed this, that in every more than 20%, there are people who do a little bit assembly error. Why? Because we have such a big, they are not stupid, but they have to produce so many variants that if they have 1 week of holiday, they come back, they forgot that this special variant, they should use another screw, for instance. So this happens. So wrong action of human. Then wrong action of robot, also quite often. Wrong interaction between a human and a robot, or a wrong interaction between 2 humans. If you go to assembly lines, you have workers working together. Or the wrong interaction between several robots, or in the end, the most complex, when we have hybrid teams of different robots and humans, of course, things happen. And this is, from the AI point of view, the field of plan recognition. It's quite an advanced field which is connected to conferences on planning, automatic planning, but this is the inverse process, because now you have to recognize what plan is he following. Is this the correct plan or the wrong plan? And often it's the wrong plan. Interaction recognition and even intention recognition, because if you observe that the worker does something which is not conforming directly to the plan, you have to find out what is his or her intention in this sense. Maybe it's a good idea to change in this specific situation really the assembly plan. So that's the problem. How do we do this? The new idea in this project is that instead of this big loop where we have production step 1 to step N, and then we have the final check, and we say, okay, we find in step K, yeah, we assume there was an error, yeah. This is very nice, but as I said, it means that then we go to the repair process, we have to return to step K, and then all the steps until the end have to be repeated. Yeah? This is very expensive, very time-consuming, and as I said, in manufacturing, for instance, in semiconductor, they throw away these components. Also, if you produce bottled water and so on, well, of course you don't do this with a BMW. It's a little bit expensive. Yeah, if you find one error, you would go and repair. But anyway, the idea is to avoid this situation, and this means that we have smaller loops, very small loops. We in every step, we check in real time, does the guy, the worker, do the right thing or not? If not, then of course it will produce an error. Yeah? And this means that we don't wait for the error effect, we look at the wrong action and then we correct. Look at the wrong action, correct, and correct, and correct. That means, yeah, we have n possible correction steps, yeah, but they are cheap because it just happens when the wrong thing has been done. So that's the idea. And why do we do this? We want to reduce the workload and the time needed for doing a correct product, energy consumption, and also there is a lot of criticism in sustainability, of course, scrap and waste. I mean, the waste production is unbelievably high. Most companies don't talk about this. It's very hard to get the numbers. If you go to a factory and look at the waste disposal, it's quite high. Especially in semiconductor, the yield is not extremely high, and I'm also involved in a company for sensor production. 70% of the sensors are thrown away because they don't work. I mean, this is, from a sustainability point of view, not a good idea. Yeah, and as you all know, it's a success, and I also, again, emphasize that the European Union really all together, not only Czech Republic and Germany, but also other European countries have to join for the next decade. I think it's absolutely necessary, because now we can really show that this is exported. Our industry in Europe depends on this, that we are leading. We don't have a lot of disciplines where we are leading, but this leading discipline we have not to neglect. We cannot give up this and jump to another area. This would be absolute nonsense. And our new chancellor, of course, Angela Merkel, supported this very much. And we were a little bit concerned what happens when she retires, because she was really a driving motor for this. But fortunately, our new Chancellor, Olaf Scholz, the first visit he did to a research institution, he came to DFKI and looked at the smart factory. And this says a lot. He really praised this, and he sees the reason why this is so important in the current situation. But let me now discuss more technically what is behind all this for the next decade. I think, of course, we have all these hardware platforms, and we go into edge, cloud, and sky computing. What is new is different software platforms. Of course, we have Gaia X with more than 2,000 companies, but my own opinion is we have to see whether this is a big success. Anyway, the direction is good. Yeah? More successful currently is Catena X. This is a project where only the automotive industry and first-tier suppliers are involved. It's more focused in a certain sense, and it fits perfectly to what we do here at Circ and RICAIP, and fits to Industry 4.0. Then we have the new ATRA. I think this is very good that we have now an association for AI, robotics, and data, because these topics belong together. This is a new association which we support very much. But now, I already mentioned sky computing, because we all learned with the current crisis, not only the chip crisis, but the logistic crisis, if you think about blocked harbors in China and so on, we cannot rely only on cloud computing. Many people say we need multi-cloud, because we have disappointment with so-called lock-in. We are in one cloud and cannot leave it. Today, as you may know, it's much more cost-intensive to leave a cloud, to delete the data, than to enter the data. This is a trick. So you are like in the prison. You have decided one cloud. Therefore, many people say we need multi-cloud. For instance, Siemens offers, of course, a multi-cloud solution, also SAP. But this is also not a lot of fun, because if you have multi-cloud, all your software has to be adapted and again to another cloud. All the APIs you have to rewrite. This cannot be a good model for the future. So the new idea is so-called sky computing. I'm involved at ICSI in UC Berkeley, and the idea came from a Romanian scientist working at UC Berkeley, and he published a lot, but it's now a reality. More and more companies are starting this so-called sky computing, and unfortunately there's a lot of sun, but I hope you can at least read it, or I say it's against the proprietary clouds. It's an idea that you have the sky computing is a cloud of clouds where everything is virtualized, so you don't have to care about individual clouds. You operate your system as if there is only one cloud system worldwide. There is no lock-in this system, because they have a compatibility layer. So all the APIs are automatically compatible between the different real clouds behind this. This is a big advantage, and it's now very much pushed by research in the United States and Europe, and I think it's inspired by machine translation. Because when people started with machine translation, they said, oh God, if I want to translate from English to Czech language, then of course we have to write a program doing this. Back the same. But then from Czech to German, again a new program, and so on. And when you calculate this, in this situation, in this diagram, you need n times n minus m different programs. This is the so-called transfer approach, which is now used in multi-cloud system, extremely expensive. When you do the so-called interlingual approach, where you have this layer which gives you virtual access to the other algorithms, then you save a lot. It's much less effort, and this is the approach which is followed in AI, which is based on the semantic level. So altogether, for Industry 4.0, we have to deal now with the sensor layer, with the edge cloud layer, which is very close to the machine. Then the so-called fog layer. These are all the edge cloud things in the whole plant of the company. And then we go to cloud. But the ultimate layer is then the sky layer. The sky, the cloud of cloud. So we have a lot of layers of virtualization. I think this is very important message, because it reduces the data volume to be transferred. Many people made the mistake that if you do everything in the cloud, then you have a massive amount of data. It's very critical for hacking. people, the security issue is very big and so on. So it's much better to do what you can on this edge layer here, where you have all the chickens, you have a lot of edges, of course, and unify this, fuse this in the fog layer, and then go to cloud and higher levels. That's the idea. It's a hierarchy, and the same we do for digital twins. We have digital twins which are very local on the edge, and then of course we can have composites. If you have a full product, for instance, a complete BMW or whatever, a complete car has a lot of digital twins, and this you can store in the cloud, yeah, but because this is not a very real-time critical, yeah. Whereas when you drive a robot based on a digital twin, this is no way that you can do this in a cloud, because the cloud is much too, takes too long. It's it's not very fast, and this is not enough. So in our Base Hinaus, it was a project we did with some companies, and Fraunhofer, DFKI in Fraunhofer has the Basis Shell system, which is in conformance with the Industrie 4.0 complete design. And this is now used, for instance, in Volkswagen in Zwickau, where we bring together the production planning and the logistics planning. And this is integrated. Before we had different processes, and this was again very inefficient, also in terms of the sustainability. Let me finish with some remarks how the edge computing is working. We even in a brownfield industry, we can add some devices so that a classical industrial scale, which we have here in the production process, is upgraded by having a small device there and connecting this with the local edge cloud by just a communication protocol like OPC UA, which is now the standard, so that we can do the retrofitting, turning an old factory, legacy factory, into a modern smart factory. And there are a lot of AI devices, edge AI devices already on the market, and of course the sensors get cheaper and cheaper, so it's really realistic. Let me mention that at the beginning of Industry 4.0 we already said, but this was a vision, it was hard to implement, and we still have not the full stack implemented today with all these things, but we say the product becomes an information container. So it, as I said at the beginning, it carries all the information about the complete supply chain in the life cycle. But very important from the multi-agent point of view, the product also becomes an agent. It can also affect its own environment. For instance, such a product, and we implemented this, can tell the robotic cripper where to crip. Yeah? You have an inverse function. Normally, the robot has to look and where should I crip this special product. But in this case, the product itself tells the robot how to handle itself. Or the product becomes an observer and says, you know, I monitor the environment, it's getting too hot here, for instance, please, I need some cooling. We implemented this, for instance, in projects with Volkswagen in Wolfsburg, where we actually were able to reduce the energy consumption more than 200 million euro per year. 200 million euro savings in energy. Why? Because these factories, they really wasted their energy in a certain sense. They go to full power of all the machines, but there is no activity. It's like having the workers, you know, run and no product is in front of them. But they have one button, they start the factory, everything is running. But from the planning view, it's pretty clear that machine X will not work in the next half hour. There is no product which has to be machined. This is nonsense. But it was very easy to implement, of course. Now we are more sensitive to energy consumption. We use really constrained processing And we also introduce, this is very simple but very efficient ideas, that you have various standby modes which save energy, that you already looking at the incremental production plan, you can say, okay, right now this machine is not needed, but in about 10 seconds it should work. So you go to another level in the standby mode, because if you are in deep standby for some machines, it takes 2 or 3 minutes until they are ready to do the machining, and so on. So a more clever model, and I cannot describe all the details, some are also confidential, but let me just summarize that even also with Bosch, we did this not only for normal, power, but also for compressed air. Again, we found with these methods, using digital twins, advanced planning algorithms from AI and optimization, you can reduce the cost of compressed air in one factory by the factor of 40. So it's, you see how much possibilities there are, and as our politicians become more sensitive to this issue, and also the society, I think it's very good application of AI in Industry 4.0. Let me finish with the following remark. We had already the first decade and a lot of success with this industrial internet. We have the first smart factories. Not all smart factories are, not all factories in Germany are smart. I think it's less than 20%. We have to be honest, It's a long way to go. There is a huge amount of industrial data. This is available, but now we have really to use AI, machine learning for this industrial data, and not only just statistical learning, but also machine understanding of what's going on. So we have in AI, for instance, qualitative physics, where we can also reason about these things is extremely important, and we have the first approaches really running. And this is the next decade, and as I said, one of the most interesting and let's say low-hanging fruit is because normally in a factory you had specialists for logistics, intralogistics. There are many architectures and also specialists on this. Then there are the planning guys for the production process, but they didn't work together. Even sometimes they were fighting, and this cannot go on. And now we have the technology to integrate, and we have already done this in Zwickau, because in Zwickau, what we saw today here with robots really bringing the emerging product to the individual machines was one of the key ideas of Industry 4.0, and it will be, step by step in the new factory this is for electrical cars, will be applied. We have a test bed first in Dresden, but then this will be as a product in Zwickau. Very important. Let me conclude. Industrial AI is, in my mind, a key driver for the next generation of Industry 4.0. So artificial intelligence becomes even more important in the context of Industry 4.0. And Professor Mazik, I think it was a very good decision to put this here, because you already have the expertise. SERC from the beginning had robotics, cybernetics, and AI integrated. For the training of the large models, which we also need, of course, we need sky computing, as I said, because here we need a massive amount of data, but not in real time. It should be transparently done in the cloud of cloud. For online learning, of course, we cannot trust cloud or sky computing. We have to go to the edge AI approach. It was very low latency, and we saw this here with 5G already implemented in the second stage of the test bed here. And finally, urban production. You already have the smart energy here on the roof, and this goes on. Zero defect manufacturing and tracking and methods of the circular economy. This is, in line with the goal of the so-called Green Deal. Green Deal, the term, I don't like it, but anyway, the direction is good. Sustainability is an issue which we take very seriously. Also, the lesson learned from the Ukraine war, really shows, yeah, that this will be a big disaster in the next years if we don't solve the energy problem. Some of our factories have to be shut down, actually. Yeah, this is terrible. Yeah, we are too much dependent on Russian energy, and we have to stop this. And this can be resolved only, yeah, with this methodology. This is my conviction. Thank you very much for listening.